Before I begin, let me just say this, that there would be almost no writing at all in this video, and it would be mostly just me speaking. So, the goal of this lecture or video is to answer this question that what the heck is quantum field theory? And so before we embark on this fruitful journey, I would like to point out or mention this quote over here by Vicky Wyckoff, and it states that there are no real one particle systems in nature. So even though we when we do physics, we idealize our situation and we solve mostly for one particle systems, but it turns out that there are no such one particle systems, right, in nature. Not even a few particle systems. The existence of virtual pairs and of pair fluctuations in the universe shows that the days of fixed particle numbers are over. And so we need a new set of framework that works for when the particle numbers are changing, right? So that is, if particles are created or destroyed. So let's actually start with the concept of wave-particle duality, which tells us that the properties of electrons and photons are fundamentally very similar. Now, despite the obvious differences in their mass and charge, so electrons and photons, they have different masses and one is charged and the other is uncharged, that is photon. Now, under the right circumstances though, both suffer wave-like diffraction and both can pack a particle-like punch, right? Yet, the appearance of these objects in classical physics is very different. So, electrons and other matter particles are postulated to be elementary constituents of nature. However, on the other hand, light is a derived concept in this case. And so it arises as a ripple of electromagnetic field, or a ripple in this electromagnetic field. So if the photons and particles are truly to be placed on an equal footing, the question is, how should we reconcile this difference in quantum world? There are two possibilities to answer this, and they are that should we view the particle as fundamental, with electromagnetic field arising in some classical limit from a collection of quantum photons? Or the other one could be that should we instead view the field as fundamental, with the photon appearing only when we correctly treat the field in a manner that is consistent with the quantum theory. And so if this later part is in fact true, should we also introduce an electron field whose ripples give rise to particles with mass and charge? So those would be electrons, right? If so, yes, if so, then why did not Maxwell, Faraday, and well other classical physicists find it useful to introduce this concept of matter fields, that is analogous to electromagnetic field? So the purpose of quantum field theory, or one of the purpose of quantum field theory, is to answer these questions, and of course many more questions. So we find that the second viewpoint, where we have this field and particle arises due to this fluctuation in this field, this viewpoint is actually the most useful one. That is, the field is primary and particles are the derived concepts that appear only after quantization of the field. So we see how photons arise from the quantization of electromagnetic field and how massive charged particles such as electrons arise from the quantization of matter fields. We will see this in quantum field theory. We also learned that in order to describe the fundamental laws of nature, we must not only introduce electron fields, but also what are called quark fields, neutrino fields, Higgs fields, gluon fields, W and Z boson fields, and, well, of course, a whole lot of others. Now, there is a field that is associated to each type of fundamental particle that appears in nature. So far, this is what we have learned from this video, that there is a field that is associated to each type of fundamental particle. Now, we are almost ready to answer this question, that what is quantum field theory? But first, actually, let's ask the question, why do we even need quantum field theory, or for that matter, any new theory, right? Well, in classical physics, the primary reason for introducing the concept of a field is to construct the laws of nature that are local. Consider the well-known laws of Coulomb and Newton, which involve action at a distance, right? That inverse square law. This simply means that the force that is felt by an electron, if you're talking quantum mechanically, but if you're talking classically, then it could be for a planet, this force changes immediately if a distant proton, in case of, again, quantum mechanics, if you're talking at subatomic level, or at a huge scale level, it could be a star. So when a distant proton or a star moves, then what happens is the force is felt by an electron or a planet. It changes. That force changes. That is our very classic old Newton's law of gravitation and Coulomb's law of electromagnetism, the interaction law of charges. Not only, in fact, that this is philosophically unsatisfactory, but it is also experimentally wrong. It turns out this way. The field theories of Einstein and Maxwell then remedy this situation. That is, they have a cure for this situation, with all interactions being mediated in a local fashion by the field. Now, this requirement of locality remains a very strong motivation for studying field theories in the first place in quantum world. Of course, there are further reasons for treating the quantum fields as fundamental. In fact, actually, I will give you two answers to this question of why do we need QFT, that is quantum field theory. Okay, so the first one, it is because of this marriage of quantum mechanics and special relativity implies that the particle number is not conserved. So we have particles are not indestructible objects. They can certainly be created and or destroyed. That is, even give an example would be when an electron and an anti-electron, that is positron, collide with each other, right? So they do not remain in existence forever. This is an experimentally verified fact and it was first predicted by none other than Dirac himself, who understood how relativity implies antiparticles. Okay, let me give you an example. Let's actually quickly sketch the circumstances in which we would expect the number of particles to change. So here I might use this paper to write some things down. It would be a very little bit of mathematics. So we are going to consider a particle whose mass is m. So consider a particle whose mass is m, and it is trapped inside a box of length L. So say we have this box and we have a particle over here. It is trapped in this box. Of course, it will not be like stationary in this box. It will be moving all the time. But its mass is m and the length of the box is L. Right? Now, Heisenberg is telling you that uncertainty in momentum would then be delta P, which is always greater than or equal to h bar over L. Right? This comes from the Heisenberg's uncertainty principle. Now, in relativistic setting, momentum and energy are on equivalent footing. So we should also have an uncertainty in the energy, and that would be of the order delta E is greater than equal to h bar c over L. Now, however, when the uncertainty in energy is going to exceed a specific amount, that amount is delta E is equal to 2mc squared. So when the uncertainty increases this much amount, then what we do is we cross the barrier to pop particle and antiparticle pairs out of the vacuum. This is when these particle and antiparticle pairs are created. That is, when the energy or the uncertainty in energy increases or exceeds by this amount. We learn that particle-antiparticle pairs are expected to be important when a particle of mass m is localized within a distance of the order that is given by lambda is equal to h over mc. Now, a distance that would be shorter than this one, at that distance what we find is with a very high probability the particle and antiparticle pairs are swarming around the original particle that we actually placed inside. Right? Okay, so the distance lambda, this one, is actually in fact called the Compton wavelength. So there's a name for it, and you might be familiar with this name, but you might have not know what or the importance of this, right? And hopefully now you know somewhat. And it is this Compton wavelength is always smaller than there is another wavelength, and that's called the de Broglie wavelength. That is lambda de Broglie, so I'm going to abbreviate it like this, is equal to h over the absolute value of your linear momentum, right? That is the de Broglie wavelength. So one way in which you could think about these two different wavelengths, that is the de Broglie wavelength and the Compton wavelength, would be something like for the de Broglie wavelength, you could say that it is the distance at which the wave-like nature of particles become apparent. And the Compton wavelength, on the other hand, is the distance at which the concept of single point-like particle breaks down completely. So at the Compton wavelength, there is no concept of this a single point-like particle, because as we just said, that at this wavelength, wavelength that is shorter than the Compton wavelength, what you see is that there is an antiparticle and particle pair that is swarming around this mass that we put inside, right? So of course then you could not talk about this single point-like particle. Right, now moving on, let me say that the presence of this multitude of particles and antiparticles at short distances tells us any attempt to write down a relativistic version of the one particle Schrödinger equation, that is indeed an equation for fixed number of particles. That cannot be done. It is doomed to failure. And there is in fact no mechanism in standard non-relativistic quantum mechanics that deals with the changes in the particle numbers. So in non-relativistic quantum mechanics, the quantum mechanics that we have been studying, in that framework, so to speak, there is no way that we could deal with this particle number changes, right? And indeed, any attempt to do so, if you go and try doing it, what happens is that this attempt meets with serious issues. Issues like negative probabilities, infinite tower of negative energy states, or even a breakdown in causality. Well, in each case, this failure is telling you something. And that is that once we enter the relativistic regime, we really need a new formalism in order to treat the states with an unspecified number of particles. And this formalism is called QFT, quantum field theory. Now, I said I'm going to give you two answers, and I have given you one of the answers to the question that why do we even need quantum field theory. The second answer is something like because all particles of the same type are the same particles. And even though if this may sound rather dumb, believe me, it is not, okay? What I mean by this is that the two electrons are identical in every way, regardless of where they came from or what they have been through, right? The same is actually even true for every other fundamental particle. Let me go ahead here and give you an example that might even seem very interesting to you. Suppose that we capture a proton from a cosmic ray, which we identify as coming from a supernova, for example, that is somewhere 8 billion light years away. Now we compare this proton with a one that we can freshly mint in a particle accelerator here on Earth. Well, if you're Michio Kaku, then you could do it in your backyard, but you get the point. And the two are these two protons, that the one which we see from this supernova that came from 8 billion light years away, and the one that we freshly made in a particle accelerator right now, these two are exactly the same. Exactly. Now, whoa, how is this possible, right? Why are there not any errors in this production of this proton? There could be errors, right? Because one is completely somewhere else and the other one is somewhere else, and the distance is not minute, it is extraordinary. So how is that the two objects that are manufactured so far apart in space and time be identical in all respects? So one explanation to this that might be offered to you is that there is a sea of proton stuff, right? So a sea of proton stuff, it fills the entire universe. And we make a proton, we somehow dip our hand into the stuff and from that mold a proton. Now then, if this is the case, then it would be no surprise that all the protons are identical, because there is a field and we are dipping in our hand in this field, and what we do is when we take out something from this field, the proton is molded in that time itself. So then if that field is the same everywhere, then we would get the proton identical every time we take it out of this field, right? And well, as we will see, this is not far from the truth, only the fact that the stuff that I'm calling it as the stuff is actually the proton field. Or if you look more closely or close enough, it is actually the quark field. Now, with all of this, we are finally ready to answer the main question of this video, that is, what is quantum field theory? Okay, so all this time, the clue is really in its name itself. And the name is, if you think about it, if you think about this name, quantum field theory, you figure it out that it is the quantization of a classical field. And let me give you a very familiar example. That would be the electromagnetic field. And in standard quantum mechanics, we are taught to take the classical degrees of freedom and we promote them to operators that act on Hilbert space. So for example, you would have a position operator corresponding to a position. You would likewise you would have a momentum operator corresponding to the momentum, right? So what you do is you upgrade these degrees of freedom with operators, and these operators then act on a Hilbert space. Now the rules for quantizing a field are actually no different than they are for this standard quantum mechanics. Thus the basic difference, or the basic degrees of freedoms in quantum field theory are operator valued functions of space and time. What this means is that we are dealing with an infinite degrees of freedom. So we would have at least one for every point in space, right? And this infinity, because we would have infinite degrees of freedom, this infinity is going to actually come back to you and it's going to bite you. So when we are doing these integrals, we find this infinity, it comes back to us and it causes us a lot of problems on several occasions, right? And well, there is a way to get past that. And that is also something that you study in quantum field theory. Now, it will turn out that the possible interactions in quantum field theory are governed by a few basic principles. And these principles are locality, symmetry, and the renormalization group flow. Now, what I mean by this is the renormalization group flow. It is the decoupling shorter distance phenomena from physics at large scales. Now, these ideas make quantum field theory a very robust framework. That is, given a set of fields, there is very often an almost unique way to couple the fields together. And this, one way or another, answers the main question, that is, what is quantum field theory? Now, you might still ask me, well, then what is quantum field theory good for? And I will start wondering if you had been sleeping all this time. Okay, no, just kidding. I'll answer this question. Quantum field theory is good for almost everything, right? And as I have stressed earlier, for any relativistic system, it is actually a necessity. It is yet still a very useful tool even for non-relativistic systems with many particles, right? Okay, so I have answered the question of what is quantum field theory, and I hope this makes sense to you now, and I hope you understand quantum field theory much better now. Of course, not the course, but the question that what it is, right? And so to end this video or lecture, I will do it so by saying that quantum field theory has had major impact in condensed matter physics, high energy physics, cosmology, quantum gravity, and believe me or not, even in pure mathematics. Now, quantum field theory, it is literally, and I mean literally, the language in which laws of nature are written.